Good. Okay, you're good.
All right. Thank you two for coming. If nobody else, if y'all want to go ahead and open up another tab and go to joinpd.com and type in that code for Pear Deck that I'm sharing on the screen, then you too can join the class. And if you've never been part of Pear Deck before, Pear Deck is just like a Google Slides or a PowerPoint, except it allows you to do stuff. You get to draw, you get to drag stuff, you get to type out an answer, that kind of thing. So we want you to have that ability. So if you'll go ahead and join to joinpd.com and type in that code that's up there. And as I go along, that code will be up there. So just in case you need that code, you can look at that code. So if you get kicked out and come back in, we can go ahead and do that. So I don't know which one of you's in, but that's good. So let's go ahead and start. And this one is going to be all about picking up where we left off last week, where we were doing Lewis structures. And then we want to talk about formal charge and polarity. So is a molecule polar or not? The geometry, which is a fancy way of saying the shape. What is the hybridization, which may be a word you're not really familiar with. And then something simple called sigma versus pi bonds. So even if you're not familiar with a little bit of this stuff, at the end of it, you'll be crazy smart sounding because you'll get to use words like sigma and pi and sp3 and sp2. So that's going to be fun for everyone. So let's go ahead and jump right into it. So a polar covalent bond happens when one thing pulls harder on the electrons in a bond. So you may remember something called electronegativity. And electronegativity is how badly one of the atoms is pulling on those electrons. So fluorine, if you were to look at a periodic table, is in the upper right-hand corner. And we know it has a very strong electronegativity for two reasons. Number one, it's got its valence electrons really close to the nucleus. Number two, it's got a bunch of protons. So two things affect electronegativity: how close the valence electrons are to the nucleus and how many protons. And that goes back to Coulomb's law. So how much is it pulling on the electrons? So this is an example of a molecule that is extremely polar. And so you get these polar covalent bonds. And that's going to come back later when you talk about intermolecular forces, because we create something called a dipole moment. And that's a fancy way to say that the electrons are being drawn to one side of the molecule more so than the other. So this is the Lewis structure for CO2. So in the Lewis structure for CO2, if you will imagine, try to think which way the electrons are being pulled. Is this a polar molecule or not? And if you're still on my screen and not necessarily the Pear Deck screen, so you got to kind of go back and forth. So right now, if you're paying attention to my screen, oxygen is more electronegative than carbon. And we know that because oxygen is to the right of carbon on the second row, and anything to the right has more electronegativity. So the electrons are being drawn from the carbon towards the oxygen. But on the other side of the molecule, the electrons are also being drawn towards the oxygen. So is this a polar molecule? And we would say probably not. And that's because one oxygen's pull on the electrons is being canceled out by the other oxygen's pull on electrons. And we can show you that pretty quickly. If I make this look like CO2, so if I make A, just like oxygen, be more electronegative, and C, just like oxygen, be more electronegative, and we'll let the B be the carbon in the middle, then what happens is the electrons are definitely being drawn to the oxygen on the left and the oxygen on the right, but notice that those poles kind of cancel each other out. So if we were looking for what is the molecular dipole, that's a fancy way of saying, is it more negative on one side and positive on the other? And what we see is, yeah, that doesn't occur. However, let's change this C molecule over here, the C atom. Instead of being really electronegative, let's make it much less electronegative. And what you can see happen is the electrons are being kind of pulled towards the B atom, and the A atom is really pulling on the electrons from the B atom. So really overall, this end of the molecule where A is ends up with the electrons more of the time. And so we would call this a polar molecule. We can even draw in charges. And you can see this end has a little bit of a negative end, and this end has a little bit of a positive end. So that's really what a polar molecule is. So here's a molecule right here, and it wants you to draw on here. If you will, using Pear Deck, if you'll go to the Pear Deck tab, and if you'll just draw an arrow between chlorine and nitrogen, which way do you think the electrons are being pulled? Think about, if you need to grab a periodic table, you can, but you can look and say, which way are the electrons being pulled between nitrogen and chlorine? Bless you. Well, welcome to the meeting. If you will make sure you mute your mic, please. And then there's a code. If you would go to joinpd.com, joinpd.com, and you can enter that code that's in the upper right-hand corner of the screen that I'm sharing with you, then that'll let you into Pear Deck and let you do some of what we're doing on Pear Deck. All right, so we had a couple of y'all draw some arrows, and let's see what those arrows look like. Okay, so one of y'all said that electrons are being drawn towards the nitrogen. Somebody else said they're being pulled towards the nitrogen. Okay, so that's pretty good thinking, and you're thinking that nitrogen is more electronegative than the chlorine. And I can live with that. If you actually looked up electronegativity values, then you would realize that nitrogen and chlorine have about the same electronegativity value. So, but if you're thinking nitrogen is more electronegative, then you can definitely think, oh, the electrons are being drawn towards the nitrogen. So the question is, does this make this a negative end and a positive end, or does this make it a non-polar molecule? Well, if we look at y'all's responses and say the electrons are being drawn towards the nitrogen, that means this end of the molecule is going to be slightly negative, and this end of the molecule is going to be slightly positive because the electrons are being drawn towards the nitrogen, in which case this would be a polar molecule. But we're going to learn that shape matters very much because this molecule doesn't actually look like a T, right? So when we think about molecules and whether they're polar or not, we're also going to have to think about what shape are they. So same thing here. Which way do you think the electrons are being pulled? To the middle, to the ends? You can go ahead and draw an arrow. You can pick whatever color you want. But which way are the electrons being drawn? Pulled to that one side. And any of you who is new to the game and not really understanding, just realize you can go to joinpd.com and type in HXIDAV, that code on the screen, and it'll let you into Pear Deck. And once you're in that Pear Deck, it'll let you draw on this slide. And let's see what we're getting. Okay, there's one person saying it's being pulled over to the right, and another person saying it's being pulled over to the right. And those are great answers. We know that nitrogen is more electronegative than carbon because it's over to the right, but also because it has more protons pulling on the electrons. So overall, we would say that this molecule is polar. The electrons are being pulled more to one end of the molecule than to another. And that's really what it comes down to. It's not because there's a lone pair on the nitrogen or anything fancy. We just want to imagine which way are the electrons being pulled. Are they being pulled more to one side than the other, or are they very evenly distributed? Okay, same thing. Which way are the electrons being pulled here? Now, this one's a little bit harder, but you would have to think, okay, well, fluorine is very electronegative. So do all the fluorines pulling on the electrons, if they all pull towards the fluorines and not towards the sulfurs, does this make this a polar molecule? Well, this one's really hard to figure out unless you know the shape of the molecule. So looking at it now, this looks like kind of a weird shape. I can't really tell whether the fluorines are going to offset each other. So why don't we stick a pin in that for now, because it's hard to decide without knowing the shape or geometry. Okay, this one right here, same thing. You got a bunch of fluorines pulling on the electrons, but what shape is this? Is it really flat? Is it like that with electrons above and below the xenon, or does it take on some weird shape like a seesaw or teeter-totter, or does it take on some other weird shape? In order for you to know whether or not something is polar, we're also going to have to include for some molecules that idea of, I wonder what shape it is. So we'll do that in a little bit. Sometimes we have molecules that you can show more than one way of drawing it. So we call those resonance structures. So up top are the two molecules of ozone. So you've got 3 oxygens. You've got a double bond on one side and a single bond on the other. But we have to draw 2 resonance structures because that really shows that the electrons aren't static. They don't just live in one place. The electrons are constantly moving around. So we talked about bond energy and we talked about bond length last time. So let's just give you a make-believe question. The double bond is shorter than the single bond. So let's say the double bond has a length of 40. And let's say the single bond has a length of 60. So 40 for the double bond, 60 for the single bond. If we were to take this molecule of ozone and actually freeze it and take a picture and measure the distance between it, it wouldn't be 40 and it wouldn't be 60. It'd actually be somewhere in between. Because in truth, this is not a double bond and a single bond, and then it flips. Since the electrons are always moving around, we would say that the distance between the oxygens is not going to be 40 or 60, but somewhere in between. So you get that idea of it's probably going to be like 50. So it's not quite a double, it's not quite a single, it's more like a bond and a half. And that's where where resonance comes in, because we know electrons just don't stay in one place. If you look down at the bottom, there's 3 different ways to draw the carbonate ion. The carbonate ion can either have the double bond at the very bottom, or on the left, or on the right. So we want to be able to write resonance structures whenever you have, say, a single bond and a double bond, and it's something that you can kind of move around. Formal charge helps us figure out what is the best Lewis structure. So sometimes you'll get a Lewis structure and you'll be like, yeah, but I could also draw it this way. So which way is best? So formal charge is pretty easy. You take the number of valence electrons minus the number of non-bonding electrons around that atom minus half the number of bonding electrons. So let's look at this molecule that's above you. Carbon right here. If you look on the periodic table, carbon has 4 valence electrons. So we would do 4 minus the total number of valence electrons, minus the total number of non-bonding electrons. Non-bonding electrons means electrons in lone pairs. So it would be 4 minus 0, because there's 0 lone pairs around carbon, minus 1/2 the total number of bonding electrons. So carbon's formal charge would be 4, number of valence electrons, minus 0 lone pairs minus 2, 4, 6, 8. There's 8 electrons totally being bonded. Because remember, every single bond is 2 electrons and every double bond is 4 electrons. So 2 plus 2 plus 4 is 8. So we go back to valence electrons 4 minus 0 in lone pairs minus half of 8 is 4. So 4 minus 4 is 0. So carbon would have a formal charge of 0. Oxygen, on the other hand, has 6 valence electrons. So what would be the formal charge of oxygen? Well, it would be 6 minus the number of electrons in lone pairs, so minus 4, minus the number of bonding electrons. Well, it has a double bond, and that's 4 electrons, so it'd be 6 minus 4 4 electrons in lone pairs minus half of 4. So 6 minus 4 minus 2 is 0. So this is a formal charge where carbon is 0 and oxygen is 0. And that really is the best we can get to. The goal is for everybody to be 0, and that's the best Lewis structure. If everybody can't be 0, then the goal is whoever is most electronegative gets to be the negative formal charge. So that's just kind of the idea there. Valence electrons minus number of non-bonding minus half the number of bonding. So let's look at an example. This is a different way to draw this very same molecule, HCHO. So let's do it the very same way, HCHO. It's just a different way to do that. We can find the formal charge for each thing. We don't ever need to worry about hydrogen because hydrogen is pretty easy. So the formal charge on carbon would be 4, the number of valence electrons, minus the 2 up here in lone pairs, minus half of 6, because there are 3 bonds around the carbon, and that's a total of 6 electrons. So that would give that a formal charge of -1. And the oxygen would be 6 valence electrons, minus 2, because it has a lone pair above it, minus half of 6, because again, there's 3 bonds around the oxygen. And since there's 3 bonds around the oxygen, that's where that 6 comes in, because each bond has 2 electrons. So we ended up with a formal charge of carbon of -1 and a formal charge of oxygen of +1. So what's a better Lewis structure, the one we had before or this one? Turns out the one we had before is much better, because when we do the formal charge of carbon ends up being 0, and the formal charge of oxygen gets being 0. So on the AP exam, oftentimes they'll give you 2 Lewis structures, and they'll say, hey, which one's best? And then they say, make sure you provide proof of, or not proof, evidence of why you think so. And the evidence is going to be based on formal charge. So you go through and you calculate the formal charge, and that becomes your data. And then your explanation or your reasoning is that formal charge of 0 is better than the formal charge of +1 -1. So if you can get everybody to be 0s, that's the dream, right? So these are all different Lewis structures for SO3. So if you could, I'm going to let you draw on there. Try to draw the formal charge of sulfur on each and every single one of those diagrams. So try to, when you draw, try to make it small. But for each one, try to give me the formal charge for sulfur for each one. Just so you know, sulfur has 6 valence electrons, just like oxygen does. So draw anywhere on the slide. What is the formal charge of sulfur in each one of these molecules? For those of you who aren't in Pear Deck yet, I know a number of y'all have joined. So if you would like to be in on the Pear Deck activity and you get to draw on there, all you have to do is open up another tab and go to joinpd.com and type in that code that's in the upper right-hand corner. And that'll give you the ability to get in. And then you can draw on there and answer questions too. So let's see what y'all are putting as answers. Nobody yet. All right. Well, let's do the first one while y'all are waiting out. Sulfur has 6 valence electrons. So no lone pairs. So it'd be 6 minus 0 minus half the number of bonding electrons. So there's 2, 4, 6, 8, because there's 2 singles in a double bond. So it would be, sulfur would be 6 minus 0 in lone pairs around it, minus half of 8. And 6 minus 0 minus half of 8 for the very first molecule that you see there, sulfur would have a formal charge of -2. No, sorry, +2. 6 minus 0 minus half of 8. And then as you go across from left to right, you'll notice that those first 3 resonance structures are all exactly the same. The only thing that's different is they move the double bond. So the sulfur in that entire first row, they're all going to be the same. They're all going to have a formal charge of +2. So see if you can figure out what the formal charge of sulfur in the second row is. And notice that all those are going to be the same as well. And you can just write right on the diagram. You can just write whatever you think the formal charge of sulfur in that second row of molecules is. Okay, I got somebody with a +1 and somebody with a 1. And somebody's cheating, already did the third one. Good for you. And somebody put a +1, that's good. Don't forget that when you're writing questions and writing answers for formal charge, I would go ahead and write +2, +1, things like that, not just 1 and 2, because you're trying to show the reader exactly what you mean. So don't be afraid to write the pluses in front of things. So let's see if +1 is right. So sulfur would be 6 minus 0 lone pairs minus, there's 2 double bonds and a single bond. So that's 2, 4, 6, 8, 10. So it's half of all the electrons in bonds. So it'd be 6 minus 0 minus 5. And that would be 1. So in the top row, the sulfur has a +2 formal charge. In the bottom row, in the middle row, the sulfur has a +1 charge. And now, because someone was already doing it, see if you can go ahead and write what the formal charge for that last one is. And that last one has double bonds everywhere. I should have moved it over just a little bit, but I didn't. I apologize. But that last one has sulfur with double bonds to all the oxygen. So everything looks exactly the same. And you can just think about what that is, and then drag the icon onto which molecule you think is the best. Based on formal charge, which molecule do you think is the best molecule to draw? Which Lewis structure does the best job according to formal charge? Just drag the icon to where you think it should be. And for the most part, y'all are getting it right. That's great. I see somebody sneaking in. But the goal here is to minimize formal charge. So sulfur in that very last molecule at the bottom has 6 minus 0 minus half of 12. So 6 minus half of 12 is 6. 6 minus 6 is 0. So the one that gives sulfur with a formal charge of 0 is down here at the bottom. But let's look and see what the formal charge of oxygen would be. Oxygen also has 6 valence electrons, minus 4 because of the 2 lone pairs around it, minus half of 4 because it's got a double bond. So 6 minus 4 minus half of 4 means the oxygen also has a formal charge of 0. And remember, the goal of formal charge is just which one is the best. You're trying to get everybody out there to have a formal charge of 0. That's the goal. Right, so y'all decide which one is the best. You can drag the icon based on formal charge, drag the icon to which one you think is the best one. This is called the thiocyanate polyatomic ion. If you need a little bit of help along the way, nitrogen has 5 valence electrons, carbon has 4, and sulfur has 6. So which one do you think is the best based on formal charge? Let's see what y'all put for responses. Oh, I got one of each. I got one that is waiting to see which one the right answer is. Okay. So let's go back and look at the thing and see what the formal charge is. If you did the formal charge of carbon in each one of these, the formal charge of carbon is 0 because it's 4 minus half of 8. In each one, there are 8 bonding electrons. So 4 minus 4 is 0. That's not an issue. Let's take the first one and figure out what its formal charge is. So this would be 5. That's how many valence electrons nitrogen has. Minus 2. 5 minus 2 is 3. Minus half the number of bonding electrons. So it's 5 minus 2 minus half of 6, because that's a triple bond. So 5 minus 2 minus 3 is 0. So this one up here gives nitrogen a formal charge of 0. Sulfur, on the other hand, on that same first molecule, it would have a formal charge of, it has 6 valence electrons, minus 6 around it. So 6 minus 6 is 0, minus half of 2, because there's one bond, that's 2 electrons. So 6 valence electrons minus 6 in lone pairs minus half of 2 means sulfur would be a -1 formal charge. I don't like this one only because if anybody gets to be negative, it should always be the most electronegative element. And if you look, nitrogen, carbon, and sulfur, nitrogen has to be the most electronegative out of those. So the second one, nitrogen would be 5, minus 4 is 1, minus half the number of bonding electrons would be, this would give nitrogen a -1, while sulfur over here would be 6, minus 4 lone pairs electrons. So 6 minus 4 is 2, minus half the number of bonding electrons is going to be 2. So 6 minus 4 minus 2, that gives sulfur a formal charge of 0. So I'm with you. I think that second one really is the best one just because it tries to get everybody to be 0 as much as possible. But in a polyatomic ion, the formal charges have to add up to be the charge of the ion. So it's okay that nitrogen's -1. We can't always have a situation where everybody is 0. So we try to get to the best one there is. And the last one isn't any good at all. So nitrogen has basically too low of a formal charge and sulfur is too high. So the idea is you're just trying to minimize it as much as possible. If you need more practice with that, and you probably do, reach out to your teachers and say, hey, can we do some more formal charge practice? Right? Somewhere in your student notes from your teacher, or somewhere when you guys go over this, you should be talking about geometry of molecules. So what is the shape of a molecule? And you should have a table similar to this. And instead of this table, I'm just going to show you what geometry is based on. Geometry is based on the idea that electrons don't like each other. They're the same charge. And if they don't like each other, they want to get away from each other. So if I take the electrons in one of these bonds, and you should be on my screen share now, not on the Pear Deck slide. But if you are, if I take the electrons in one of the bonds and try to move them to get close to the other bond always runs away. And where does it settle out? It settles out exactly opposite of each other. And this is something we call VSEPR, or VSEPR, valence shell, the outermost electrons, electron pair, so the electrons that are out there, repulsion theory. The electrons really don't like each other. So if I have a molecule like this with just two bonds, it's going to be something called linear, and it's very much a linear molecule. I can even rotate this, and I can show you that it is indeed a straight line. If I were to throw in a lone pair to this, notice that that bends the molecule. So you have a molecule that's bent, and that's because that lone pair is actually pushing down on the electrons in the bonds. And we can even measure the bond angles, right? So we can look and say, all these electrons should be 120 degrees from each other. Now, what happens if I add in a third thing? So now let's stick three things to it. Those three things stuck to it is like part of a circle. So how do you get three things as far away from each other as possible in a circle? And we would call that a 120-degree angle. But here's what I want you to notice. Notice that this thing is totally flat. And because it's totally flat, we use the word planar or planar, and that means everything's in the same plane. And trigonal means it's three-sided. So you've got one side, two sides, and then three sides, right? So if you add electrons to this, then of course now it's going to start bending things around. And when you start bending things around, you get different shapes. So this is no longer planar. If you look at it, it looks more like kind of a space alien, but it's got a pyramidal shape, because if you look at it without the lone pairs, every single one of these bond angles kind of comes down. And then if you look at the bond angle, it's no longer 120 degrees. All the things kind of got smushed slightly closer together. So this is the basis behind VSEPR theory. And if you ever want to play with this, you can go to something called PHET, P-H-E-T, which is the website I'm on right now. And you can look at a molecule shapes. It's called molecular shapes. And you can play with this as well. You can also be absolutely ridiculous. You can add a whole bunch of triple bonds if you want to, and you can make some weird shapes, and you can move things around if you get so excited about it. But realize you can't have that many triple bonds. That's just ridiculousness. So if we go back to the Pear Deck, and you're going to need to memorize these shapes at some point for the AP exam. So it's really good practice to build these molecules, play with the PHET thing, and try to imagine them in your head. Try to say, how are all the electrons going to get as far away as possible? I mentioned before that not only polarity, but we can also talk about bond angles. So let me show you a bond angle of something. This is a molecule called methane, CH4. So let's see what the shape here is. The shape is something called tetrahedral, meaning it's got four sides. And if we look at the bond angle in 3D space, this would have a bond angle of about 109.5. That's because in a three-dimensional space, that's as far as those bonds can get away from each other. is to get to about 109.5. So 4 things bonded to it is about 109.5. But what happens if I lose one of the things and drop in a lone pair? So do you think the bond angle is still going to be 109.5? Well, let's see. When you add a lone pair, like this NH3 molecule on the Pear Deck slide, that lone pair smushes it a little bit more. So having a lone pair above something actually smushes that bond angle just a little bit more. And water over here, H2O, it's going to get smushed even more. So the good notion is if you add lone pairs to something, it's going to squish the molecule together a little bit more. So this is that water molecule we were just talking about on my screen share. And if I showed you the bond angles here, they're not really 109.5. You would have to actually go to real molecules. And if you looked at real molecules, in essence, this is 104.5. So it's not really that, it's not the, well, it should be 109.5. When you add a lone pair, it gets a little bit more squeezed than if it was just bonds. So you'll make sure you kind of understand that idea. A lot of times on the AP exam, they'll say the bond angle is 109.5. What is the bond angle for something like NH3? Well, you can't say less than 109.5 because 2 is less than 109.5. So if you want to guess 107, 105, if you want to guess a number slightly less than 109.5, that's fine. But don't just say less than 109.5. Most of the time, if you have to guess an angle, they're going to give you a range. So 105 to 110 or something like that. They'll give you a range of numbers you can pick from. So try not to use that less than thing all the time. All right, so here's a Lewis structure. So what is the shape of this molecule, do you think? So you can type out your response in Pear Deck. What shape do you think this molecule is going to be? What is its geometry? You can type that out on Pear Deck. Just what do you think it is? You don't have to use the official words if you don't want to. So if you think it's going to kind of be like bent or something like that, or if you think it's going to be tetrahedral, and you may even want to pull up in another tab, like you may just want to type in molecular geometry and find your own chart of all the different shapes and what they can be. So for example, there's one, you can find one of your own, but it'll kind of help you realize what shape it should be. So let's see what y'all said. I got a 120, I got a tetrahedral, okay? And so let's see what the real shape of CO2 is. And if we, let's see, if we want to do CO2, so let's say I need carbon in the middle, and then I need a double bonded oxygen on one side and a double bonded oxygen on the other. And if you look, this shape is actually linear because the oxygen on each side tries to get as far away from each other as possible. And that makes sense. There's no lone pairs around the carbon causing the shape to be bent or anything like that. So when you're looking for lone pairs, don't think about the lone pairs on the oxygen. They're not really affecting the shape so much. Look at the lone pairs on that central atom. So this one would be linear because that makes the most sense, directly in a line. Okay, what about this one? We did this one last week. We drew SF4. What shape do you think that might be? And you can type anything you want to. We just want to know, because we learn better by making mistakes and finding things out. So whatever you think the shape might be. I got a tetrahedral and a tetrahedral. So on my screen share, let's see if this thing is going to be tetrahedral. So normally a tetrahedral looks like this. Tetrahedral is 4 things bonded to that central atom. So it looks kind of like this, kind of like a tripod. That would be tetrahedral. So we need 4 things bonded to the central atom. But if you look at the Pear Deck presentation, we do have 4 things, but we also have a lone pair. So what is that lone pair going to do to that tetrahedral shape? Well, I bet you it's going to bend it into a different shape. So if I throw that in there, notice that now this thing no longer looks tetrahedral. This is actually called seesaw. And you probably, I called it a teeter-totter when I was a kid, but at a kid's playground, you know, you've got the thing where it's like seesaw, seesaw. So you kind of get that idea of that extra electron pair bends that shape. And this is just something you kind of have to work with. And as you get closer to the AP exam, it's something that's non-mathy that you can just sit and study that chart and you'll know your shapes. So that actual one would be teeter-totter or seesaw. You don't want to use teeter-totter because they won't know what that is, but you can use the word seesaw. All right, what shape do you think this one would be if you had to guess? If you think it looks like a T, or if you think it looks like maybe that flat trigonal planar thing or something like that, you can write that. We've got a tetrahedral and we've got a trigonal pyramid. Those are both excellent answers. So let's see what this molecule, is it trigonal pyramidal or is it pyramidal? I mean, or is it tetrahedral? So let's, we've got 3 things stuck to it and 1 lone pair around the central atom. Again, I'm not worried about the lone pairs around the chlorine. I'm just worried about the lone pairs around the central atom. So I'll give me a lone pair and 3 things stuck to it. And that's where we get that crazy space alien thing of trigonal pyramidal, right? Now the electrons are in what's called a tetrahedral thing. But remember, the difference between trigonal pyramidal and tetrahedral is tetrahedral has 4 things stuck to it and no lone pairs, whereas trigonal pyramidal is 3 things stuck to it and 1 lone pair. All right, let's jump around. So what shape do you think this one might be? If you were going to try to imagine this, what shape do you think this thing might take? It's got 4 things stuck to it and 2 lone pairs. So what shape might this thing take? I got a square planar and a flat box. Flat box and square planar, same answer. That was a good description. So let's see if that's actually true. Some of y'all are thinking, I think I could turn it into a double trigonal pyramidal. You could make up some stuff. But let's see what it actually is. 4 things stuck to it with 2 lone pairs. So I've got 4 things stuck to it, 1, 2, 3, 4, and 2 lone pairs. And if you look, those 2 lone pairs make all of the things stuck to it kind of live in one plane. So we call this planar because it is flat, right? But it's square planar. So with that 1 extra set of lone pairs, that kind of squeezes it from both ends, causing the whole thing to be flat. If we only had 3 things stuck to it, and 2 lone pairs, that would cause the shape to be slightly different. So this would actually be something called T-shaped. So just keep in mind that as you study this, it's something you can work on to try and memorize those shapes, because this is a very easy point to get on the AP exam. The next thing I want to talk about is hybridization. When we take a molecule and we look at how long the bonds are and the bond energy, what we find is it's not the bond energy of an s orbital, and it's not the bond energy of a p orbital. It's somewhere in between. So we do what's called hybridization. Hybridization is a fancy way of saying we mix together an s orbital and two p orbitals, and we create 3 spots in the red boxes, 3 spots to put electrons. So if I hybridize the 2s and 2 of the 2p orbitals, I'll get 3 sp2 orbitals. Notice I got one left over. We don't need that one, but that would give us 3 places to put electrons. So when we're talking about hybridization, this is very simple. Your choices are either going to be sp, sp2, or sp3. Those are your 3 choices all the time. So you're either going to mix together an s and a p, or an s and 2 p's, or an s and 3 p's. So let me show you the fast and easy way to do this. Point at the carbon and ask yourself, how many things is carbon stuck to? 4. All right, if it's stuck to 4 things, and how many lone pairs are on that, add that in. So 4 plus 0 lone pairs is 4. Then to figure out its hybridization, you take away 1 finger for the s. So you've got 4 fingers up because there's 4 places where you need electrons. So you take away 1 finger for the s orbital, and that tells you how many p orbitals you need. And that's why that carbon is sp3 hybridized. If you look at the C in the molecule that's red, what is its hybridization? Well, how many things is the carbon stuck to? 2. Stuck to a carbon and a nitrogen. And if it's stuck to 2 things, how many lone pairs are around the carbon? Add that in. 0. So 2 plus 0 is 2. Take away 1 finger for the s, and it tells you you need 1 p orbital. So this is going to be sp hybridized. We can do the same thing for the nitrogen. The nitrogen is going to be 1 thing stuck to it plus 1 lone pair. And if you're holding up 2 fingers, you take away 1 for the s orbital, and it's going to be sp hybridized. That's all you have to do. Count up how many regions of electrons are around it. Doesn't matter if it's a triple bond or not. That's 1 region of electrons, and that's how you decide what its hybridization is. So here's a molecule right here, and which atom on there, which carbon has sp3 hybridization. So you can draw anywhere on this slide. You can draw an arrow or a smiley face. Which carbon has sp3 hybridized? And just to remind you, how many things is it stuck to? Hold up that many fingers, plus how many lone pairs are around just that atom, and then subtract 1 finger for the s, and it tells you how many p's you need. So which carbon is sp3 hybridized? Okay, and somebody picked the right one. This carbon right here has 4 things stuck to it, plus 0 lone pairs is 4, minus 1 finger for the s becomes sp3 hybridized. So on the next slide, what is the hybridization of the oxygen at the very top? This oxygen that has the double bond. What is the hybridization of the oxygen there? And you can just draw that right on the slide. What would the hybridization be? Number of things it's stuck to, plus the number of lone pairs. Hold up that many fingers. Take away one, and that tells you how many P's to use. Okay, I got an sp2. Okay, got a 1p. Got a 1. So again, for this oxygen up top, it's going to be, and you can do it with me at home, the oxygen has one thing stuck to it, the carbon. It's got 2 lone pairs, so that's 3 regions of electron density. You take away 1 finger for the s orbital it uses, and that's going to be sp2, right? And if you did the carbon would also be sp2. What I want you to remember is when you have that leftover p orbital, so like this example right here, when you have a leftover p orbital that you don't use, that's always going to be used to make a double or triple bond. So for example, this carbon has sp hybridization. That means it has 2 p orbitals left over it doesn't do anything with. Those leftover p orbitals, that's what we use to make those double and triple bonds. So anytime you have all single bonds, it's usually going to be sp3. All right, so last one, what is the hybridization of this oxygen on the far right? So the oxygen hooked to the hydrogen. What is the hybridization there? So again, how many things is it stuck to? Plus the number of lone pairs. Hold up that many fingers. Subtract 1 finger for the s orbital, and that tells you how many p orbitals you need to use. So you can just write on there what you think it is. Okay, I got to type in there a sp3, a 4p3. Right? So remember here that your choices are either sp or sp2 or sp3. You don't have to worry about 4s and 6s in front of things. Your choices are always sp3, sp2, and sp. And that's because we're talking about the valence electrons, and the choices for valence electrons are going to be in the s orbitals and in the p orbitals. We don't care what energy level they're in because we just know that they're valence electrons. Those are the only electrons that we show when we're actually writing out Lewis structures is the valence electrons. So no need to put a 4 out in front of things. So it would be sp3 hybridized. And notice there's no double bond in this oxygen. That's because we used all the p orbitals. So we created 4 orbitals, 4 hybridized orbitals called sp3 orbitals. And those electrons are being used for the lone pairs in the bonds. And what's important about hybridization is they're all the same size, they're all the same length, and they're all the same energy. And we only get that when we mix orbitals together. And the last thing that we need to talk about is sigma versus pi bonds. So here's what I want you to imagine. A sigma bond is where you have an orbital with electrons in it, and another thing has orbitals with electrons in it. And instead of jamming them together, they kind of let the regions overlap. So if you're looking at my camera right now, it's kind of like the 2 orbitals, the 2 regions of electrons kind of overlap. So I'm grabbing my arms. That overlap is a single bond. So when 2 orbitals overlap like that, we call that a covalent bond, right? And those electrons are being shared. And that first one that forms is always called a sigma bond. And it runs right in between the 2 atoms. A pi bond exists when we have a double or triple bond. So if you have a double bond, it's 1 sigma, the first one that forms, and then you've got a region above and below it where you're going to have some electrons. And that's where those unused p orbitals, the ones we didn't hybridize, that's where they come into play, right? So all you have to do is look and say, if it's a single bond, it's a sigma bond. If it's a triple bond, it's a sigma and 2 pi's. It's just that easy. So on an AP exam, they could very easily ask you this, and it could look something like this. How many pi bonds do you see? In this whole molecule, whatever this molecule is, how many pi bonds do you see? And you can type out your response. Right. So while you're thinking of your answers, if you look at this bond with the number 1 by it, that's just a single bond. That's one of those sigma bonds that occurs when those things overlap. Every hydrogen tied to a carbon, those are all sigma bonds. So bond number 2 is also a sigma bond. Bond number 3 over here is a double bond. That's made up of 1 sigma and 1 pi. So what I see right here is this is the carbon oxygen right here. This is a sigma and a pi. And this carbon-carbon double bond is also 1 sigma and 1 pi. So how many pi bonds do I see in the entire molecule? Just 2. So 2 would be the answer. Anytime you look at a molecule, all you're going to have to do is think, how many double bonds, how many triple bonds, add up the number of sigmas and pi's, and that will let you answer the question. Now, here's my question for you. If you look at bond 3, so I'm looking at the bond 3 and the carbon it's connected to, we should be able to answer a bunch of questions about it. So what have we talked about today? Well, we should be able to talk about, is that a polar bond or not? And the oxygens pull harder on the carbons. That's fine. So yes, that oxygen is going to be a little bit more negative, and the carbon's going to be a little bit more positive. So polarity. You ought to also be able to calculate the formal charge of both that carbon and the oxygen. That's something else. They might ask you, what shape is just this region around that carbon? So it's got 2 things with single bonds and a double bond. And so it may want you to say, oh, its geometry is whatever. The next thing you have to be able to do is you have to be able to know the hybridization. So what do you think the hybridization of that would be? And then finally, they would want you to say, hey, how many sigma and pi do you have? So once you draw Lewis structures, there's tons and tons of things they can ask you. So it's kind of like a building block for you to build stuff. But for me right now, what I'd like to know is, what is the hybridization of that carbon that's double bonded to the oxygen? So if you could type out your answer, what is the hybridization of that carbon stuck to that oxygen? Remember, your choices are SP, SP2, and SP3. What is the hybridization of that carbon that's double bonded to the oxygen? Got a SP3, SP2, and SP1. So good news is we got all the choices, right? So do it with me. So get your fingers ready. How many things is the carbon stuck to? 3. How many lone pairs are around the carbon? 0. So the way you do this is you take away 1 finger. You take away 1 finger for the s orbital, and that tells you how many p orbitals you need. Matt, my phone's downstairs charging, so I'll have to go down and look at that, but I will. So the key here is you ought to be able to answer all these things. And this particular one is sp2 hybridized. And you could also calculate formal charge and all of those other things. So whenever
I'm going to interrupt you for just a second. I've got to leave. Just make sure everybody logs off before you close the session. That's all.
Okay. All right, cool. Anyway, so when you look at these molecules like this, it's really just a matter of taking everything and kind of synthesizing it together to think about shapes and formal charge. And this is something that's not mathy. And so for those of you who have struggled with some of the calculations of AP chemistry, this is a place where you can really find lots and lots of points. So if anybody has any questions, I'll be more than happy to stick around and answer them. I'm also going to let y'all draw anywhere on this slide. I'm not going to show them to anybody. So just in case you want to put a smiley face or something on the slide, keep it clean, because of course. But thank you guys for coming out today so much. And next week we're going to do this again, but it'll be Unit 3, the very beginning of Unit 3 with intermolecular forces, and it'll be Thursday at 1 o'clock. Other than that, we're done for today. Thank you so much.